I welcome you again for this NPTEL online course on earthquake geotechnical engineering. We are at lecture number 48, that is module 5th of this course, which is on slope stability in retaining walls. We already covered 2 chapters from this module, introduction to retaining walls, and the second chapter static pressure, that is basically out of this module, like slope stability have the 5 lectures, and then we have the 6th lecture. So, this is basically chapter number 6, which is static pressure on retaining walls. We continue, and once we finish static pressure on retaining wall, then we will come seismic pressure on retaining walls. So, static pressure we have already started from the last lecture, and we continue from the last lecture, lecture number 47, static pressure on retaining walls, where we already discussed Rankine theory and Coulomb's theory. Now, we are going to talk about 2 more the approaches for static pressure on retaining walls. One is what is called logarithmic spiral method, and the next is stress deformation analysis. And once this is over, static pressure will be over, then we will talk about dynamic pressure, then response of retaining walls, then seismic pressure on retaining walls, then yielding walls, and then we are going to talk about Mononobo-Okubo method, which is active earth pressure and passive earth pressure. Coming to this, because all the topics, let me acknowledge that most of the information is from the Kramer's book. Coming to a logarithmic spiral method, in the case of logarithmic spiral method, in case of Rankine theory, or you have the passive the Coulomb's theory, we assume that your this Feller surface is linear. That means, in this case we have assumed that this is a straight line, this was a straight line if you recall that. However, here it is assumed a curve, and in this curve what is done, you have logarithmic spiral curve initially, and then you have a straight line. So, this is the basic difference between the logarithmic spiral method and other methods. So, why it is required? Although the major principal stress axis may be nearly perpendicular to the backfill surface at some distance behind a rough, that is delta, when the delta is greater than 0 wall, the presence of shear stresses on the wall soil interface can shift its position near the back of the wall. If the inclination of the principal stress axis varies within the backfill, the inclination of the Feller surface must also vary. In other words, the Feller surface must be curved. So, in fact, this is for accuracy, the Feller surface will not be linear, which is assumed in case of Rankine theory or Coulomb theory, rather it will be curved. A logarithmic spiral function has been used to describe such curved Feller surfaces for active as well as passive earth pressure condition. The active earth pressure distribution is triangular, which is we just seen the figure, for walls retaining planar cohesionless backfill. So, this is for the again for cohesionless backfill, that means we are assuming C equal to 0. When the C equal to 0, then you get this kind of variation. The active earth pressure coefficients given by the log spiral approach are generally considered to be slightly more accurate than those given by Rankine or Coulomb theory, but the difference is many times so small that the more convenient Coulomb approach is usually used. Rankine theory greatly predicts actual passive earth pressure and rarely used for due to this reason, because it is underestimating, while Coulomb theory overestimates, and this overestimation is being unconservative. An unconservative error is there, over predicts passive pressures by about 11% for delta is 5 by 2, and about 100% if your delta friction angle is equal to 5. So, Coulomb theory error compared to logarithmic spiral will depends on the delta value. For the low value of delta, error is small, but for high value of delta the error is large. So, this was about logarithmic spiral method. Now, for static pressure, there is stress deformation analysis also. Since the actual pressure that act on retaining walls depends on interaction between the wall and the surrounding soil, which we have discussed. So, that means this is nothing but this is basically this we can call it as delta, that depends on the value of delta. It seems logical to expect that they could be estimated by stress deformation techniques such as the finite element method. Finite element analysis are in fact very useful for estimating retaining wall pressures and movements. So, the finite element analysis is used for stress deformation analysis, and here we can calculate wall pressure as well as movement. I mean, that means basically deformation. The accuracy of stress deformation analysis, however, depends on how well they are able to model the actual field conditions. So, depending on the actual field condition, this can be modeled. A useful method of analysis should be able to describe the stress distress behavior of the soil, which is nonlinear, and wall usually assumed to remain linear. The stress displacement behavior of the soil wall interface and the sequence of wall construction and backfill, how it is placed. Without careful attention to each of these factors, the results of finite may have limited applicability. So, when we carried out in stress deformation analysis, finite element analysis, then we need to give the attention to these factors. Now, this chapter number 6 is over, and we are going to talk about seismic pressure on retaining walls. But before we talk actual seismic pressure on retaining walls, one of the issues is dynamic response of retaining walls, that when the retaining wall is subjected to dynamic loading, then how they respond. So, we are going to discuss in brief. The dynamic response of even the simplest type of retaining wall is quite complex. Wall movements and pressures will depend on the response of the soil underlying the wall. So, you have the soil, and below the wall there is soil. How this soil movement takes place accordingly. The response of the backfill, the inertial and flexural response of the wall itself, and the nature of the input motion. The test and analysis, the majority of which have involved gravity walls, what that has indicated, the wall can move by translation or rotation. So, there can be movement of the wall either by sliding or it can rotate. The magnitude and distribution of dynamic wall pressures are influenced by the mode of wall movement, that is mode of the wall movement, whether wall is moving in the translation mode or rotation mode. The maximum soil thrust which is acting on a wall generally occurs when the wall has translated or rotated toward the backfill. The minimum soil thrust which occurs when the wall has translated or rotated away from the backfill. So, the soil thrust will be the minimum when the either wall is translated or it rotate away from the backfill. The shape of the earth pressure distribution on the back of the wall change as the wall moves. So, when there is a movement of the wall, accordingly the shape will change. Dynamic wall pressures are influenced by the dynamic response of the wall and backfill and can increase significantly near the natural frequency of the wall backfill system. Increased residual pressure may remain on the wall after an episode of strong shaking has ended. So, this was the dynamic response. Given these complex interacting phenomena and the inherent variability and uncertainty of soil properties, it is not possible to analyze all aspects of the seismic response of retaining wall accurately. As a result, simplified methods that makes various assumptions about the soil structures and input motions are most commonly used for the seismic design of retaining walls. What are those assumptions for seismic pressures on retaining walls? So, we will discuss first some assumptions are made, what are the assumptions, and then we will discuss one. One common approach to the seismic design of retaining walls, which involve estimating the loads imposed on the wall during earthquake shaking and then ensuring that the wall can resist those loads. So, this is the way, like in static case also we said the design will be not done based on the deformations, rather what you do, the design is done based on the forces and you assume with some factor of safety, so that the deformations are within the permissible limit. In the similar case here, in the case of seismic pressure also, you estimate the loads which is imposed on the wall during earthquake shaking, and then we need to ensure that these forces are, the wall is sufficient enough thick to resist these loads. Because the actual loading on retaining walls during earthquake is extremely complicated, seismic pressures on retaining walls are usually estimated using simplified methods. So, what are the simplified methods? Retaining walls that can move sufficiently to develop minimum active or maximum passive earth pressure are referred to as yielding walls. So, the yielding walls are those walls they can move sufficiently, that means they have like flexible, they can move. So, as a result there could be development of minimum active earth pressure or maximum earth passive pressure. The dynamic pressure acting on yielding walls are usually estimated by pseudostatic procedure that share many features of those described by seismic slope stability analysis. We have already discussed in the details seismic slope stability analysis using what we call as pseudostatic analysis. So, this pseudostatic word is common between slope stability as well as retaining walls. So, this using pseudostatic procedure, seismic pressure of the yielding walls is calculated, and in these procedures what is the methodology given? There is a what is called Mononobe Okabe method, which is called in the short MO method, which is also called MO method. This MO method was proposed by Okabe in 1926 and Mononobe and Matsuo 1929, which developed the basis of pseudostatic analysis. As we discussed that this is based on the pseudostatic analysis of seismic earth pressure on retaining structures that has become popular, known as the Mononobe Okabe method, MO method. The MO method is a direct extension of the static Coulomb theory to pseudostatic condition. So, you can say MO method is nothing but static Coulomb theory plus pseudostatic analysis. For the in a MO analysis, pseudostatic accelerations are applied to a Coulomb active or passive waves. The pseudostatic soil thrust is then obtained from force equilibrium of the waves. So, what is done here? The forces which is acting on the waves in dry cohesionless backfill, cohesionless means C equal to 0, and this is shown in this figure. So, in what is shown here, you have all the forces as a static case, but two more forces are added here compared to static case. One is KHW, which is the lateral force acting outward for active earth pressure condition. KHW will act away from the backfill, and KVW it could be upward and downward. So, it is in this case assumed upward, but in the KHW will be always considered away from the backfill for the case of active earth pressure condition. Here what is KH and KV? KH and KV are nothing but they are dimensionless pseudostatic coefficients, which is same as we discussed in case of seismic slope stability. When we talk about seismic slope stability, we discuss in detail what is KH and KV. In addition, the forces that exist under this waves is also acted upon by horizontal and vertical pseudostatic forces, and these forces are nothing but this is mass multiplied by AH. So, basically what you have, you can say like this, your FH, you have FH equal to nothing but KH into W. What is KH? KH is AH by G into W, or this can also be written W by G mass multiplied by AH. So, this is the same thing. Similarly, FV is nothing but KV into W, where KV was nothing but AV by G into W. Again it can be written M into AV. What is AV? AH and AV are horizontal and vertical acceleration acting. So, ultimately because W is known, so if you know KH then you can find FH, if you know KV then you can find this one. So, that means once we know the KH and KV pseudostatic coefficient, then we can calculate these forces. And how to fix the pseudostatic coefficients we have discussed in detail when we talk about seismic slope stability. This can be linked with the seismicity of the area. Basically, we can link with the seismic zonation, seismic zone of the country. If you are in the higher zone, then assume the value of KH higher. In fact, KV is typically taken half of the KH or 2/3 of KH, but KH we discuss that it can be taken as 1/3 to half of the value of your this seismic zone factor. So, value of A max by G. So, if you know the A max by G, so 1/3 to half can be taken kh. We discuss in detail when we talk about that. So, this was about active earth pressure condition. If we draw the force polygon for active earth pressure will W will act always downward, then Kf is acting along this direction and KHW horizontally outward, KVW upward, and then you close the polygon with PAE. So, you close this. So, from this point to this point you come. Here PAE is the active earth pressure which is shown here, including the effect of earthquake. So, for the dynamic case, and PAE is given from this relation half KE gamma h square into 1 minus KE, where the total active can be expressed in form similar to the developed for static condition. So, this equation gives you a combination of total, this is total means static plus dynamic. So, this equation gives you the complete earth pressure including static also. And what is KE, where the dynamic active earth pressure coefficient KE is given from this relation, where phi, theta, psi, there are 4 angles, one is delta, theta, phi and beta, which is same as we discussed in the static case, and which is shown on the wall. But what is psi? Now the issue is what is psi here? Delta, theta, phi and beta are the same, but one more angle is involved here which is psi, and psi depends on your seismic coefficient. Psi can be found out from this relation tan inverse kh 1 minus kv, where kh and kv are the seismic coefficient. Even if I assume kv equal to 0, in that case psi could be simply tan inverse kh. This will be the case when kv equal to 0. And as we discussed earlier, you can assume kv equal to 0, but kh is not 0. However, you cannot do reverse, that you assume kh equal to 0 and kv is not 0. So, you need to consider value of kh in any case. So, as a result numerator here cannot be 0. So, tan inverse you can find, and another condition you need to check, that the difference of phi minus beta should be greater than psi for the seismic case, and gamma for the will be considered as gamma d here. So, everything is known in this equation. So, you can find the value of Ke. Once Ke is known, you put in the top equation, find the value of PAE, and now you need to find the angle alpha AE with the horizontal where this is acting, the Feller surface. So, Feller surface. So, the alpha AE is given from this relation phi minus psi plus tan inverse tan this phi minus plus C1e and C2e. What is C1e and C2e? C1e and C2e is given from these relations, where you have again 5 angles, now instead of 4, 5 angles, phi, psi, beta, then you have theta, and then you have delta also. So, 5 angles are involved, and this is based on all the angles. Similarly, C2e 1, 2, 3, 4 and theta is phi, psi, theta, then you have beta 4th angle, and delta is not coming here in this equation C2e. So, in the delta was coming in the top equation. So, although the MO analysis implies that the total active thrust should act on at a point h by 3 above the base of a wall of height h, but that will act when you have the static case. Experimental results suggest that it actually acts at a higher point under the dynamic loading condition, and that is okay, because the dynamic load will carry the load on the top. Now, how we determine the location where this load acts? So, for that what we need to do, we need to divide the total thrust acting in the static component and the dynamic component. So, we already calculated the value of PAE and PA from static conditions. So, what we do, we find delta PAE using this equation, which can be find out simply PAE minus PA. So, using this you find the value of delta PAE, and now PA is acting at h by 3 and delta PAE is normally considered to be acting at approximately the dynamic component by Seed and Whiteman recommended that it approximately at 0.6 h. The total thrust will act at height h above the base, where this is the contribution coming from the static component and this is contribution from the dynamic component divided by the total pressure. So, using this you can find the value of h from the base where this total thrust is act. and naturally the answer will come somewhere between h by 3 to h by 2. So, it will not be past the middle path. The value depends on the relative magnitude Pa and Et, but often ends up near the mid height of the wall. Seed and Weidman concluded that vertical accelerations can be ignored when the MO method is used to estimate PAE for typical wall designs. So, this was all about active pressure. Similarly, you can have passive earth pressure on the same line as we discussed for active earth pressure. And in the case of passive earth pressure, total passive thrust which act on a retaining on a dry cohesion-less backfill, again when we say cohesion-less backfill means it is C equal to 0. For the C equal to 0, it is given by PPE, KPE gamma h square by 2 1 minus kV. It was, if you recall, it was in the earlier equation it was plus, it was same 1 minus kV was there. So, here, but the difference here that Kp is given from this relation here now. So, it was Ke earlier, and again when you find the value of Kpe, all 5 angles are coming, phi, theta, psi, delta and beta. So, using 5 angles, the definition of psi is same as we discussed. In case of psi can be calculated tan inverse, you have 10 kh divided by 10 1 minus 10 kV. So, the definition remains same as we discussed earlier. So, here kh tan inverse kh 1 minus kV, kh 1 minus kV. So, this may be like okay, I think I need to erase this one. So, this is psi tan inverse kh divided by simply 1 minus kV. So, using this equation you find the value of psi, and Kp is given from this relation. Here the triangular waves, now the difference between active and passive pressure, that the KHW will act inward, it was acting outward in this direction. As for KVW, whether you consider upward or downward, that does not make a difference, but in the passive earth pressure condition we need to apply the value of KHW in upward in the inward direction, that is means towards the backfill. W will act downward, alpha p, now earlier PP was acting here like this, but now it is on the top of here. So, this was PA, if you recall PA was acting like this, and F we will make an angle. So, all are known, delta, theta, beta, phi, alpha p is not known which can be calculated. So, first of all alpha p, and then if you draw the force polygon, so this will be force polygon, F will be like acting here. So, F will be in this direction here, and from that KHW inside and then KVW in top, and then you close the polygon from this. So, this is the direction of PP can be found. What is the value of alpha p? Alpha p can be calculated from this relation which is psi minus phi plus tan inverse this. So, you have 1 angle, 2 angle, and then beta third angle, and then phi, then you have 1, 2, 3, and then last angle is here beta, like 1, 2, 3, and then you have another angles involved. So, all 5 angles are involved here. So, 5 angles are here, delta, theta, beta and phi and alpha p. Delta is coming in this case, yeah, delta is here, then psi is coming, theta is coming, phi is coming, beta is coming. So, all 5 are involved here in calculating alpha PE. So, alpha PE is calculated from this. So, with this and then PP total force will be like in case of active, here also it will be PP plus delta PE, where PP is static passive pressure and delta P is dynamic component which can be found, and the dynamic components acts in the opposite direction of the static component, thus reducing the passive resistance. So, this will be the total active thrust. This is similar, it is similar way as we discussed for in case of active earth pressure. So, with this, thank you very much for your kind attention. This was about seismic earth pressure, and then we will continue for the retaining wall in the next lecture.